Day 53, Honors Physics, Rotational and Translational Equilibrium, Torque. This problem here, number 14 in this problem set, it might be the hardest one in this particular set of problems. You have two spheres of unknown mass, but we know that one is twice the radius. So I'm starting over here on the left. We have one sphere made of the same material as the big sphere, half the radius. There's double the radius for the bigger sphere. But the key to starting the problem is the formula for the volume of the sphere. Volume of the sphere is 4/3 pi r cubed, and the key here is r cubed. So we have the volume, that's volume, is proportional to the cube of the radius. What that means is this: if you double r, that's r cubed basically in the formula, well, 2 cubed, 2 times 2 times 2 is 8, so V octuples. You don't see that word too often. V gets 8 times bigger. We have 8 times the volume. So V2, the volume of the big sphere, is 8 times the volume of the small sphere. And if they're made out of the same material, that means the weight of the big sphere is 8 times the weight of the small sphere. So it really won't matter what their weights are in particular, but the ratio of the weights is very important when calculating the torque. We have 8 times the weight in the bigger sphere. Now, over here on the far right, I have hopefully a correct picture of the actual apparatus. We have these two spheres connected by a rod. The rod actually is 12 centimeters long, so from the edge of one sphere to the edge of the other sphere, it's not going from center to center. It's going from surface to surface. So that's 12 centimeters long. So the little sphere, radius of 4, but have a diameter of 8 centimeters, and the big sphere, radius of 8, diameter of 16 centimeters. So the whole thing is, what, 36 centimeters wide, the whole apparatus. But the main thing is you put the weight of each of the spheres at their center of gravity, which would be the dead center of that sphere. So translating it down to our simplified torque diagram here, where this red line represents our entire apparatus squished down into a lever, where this is lined up with the center of the small sphere. That's weight number 1, the small sphere. That would be 4 centimeters from the edge of my computational apparatus here. And over here, lined up with the center of the big sphere, is 8 times the weight of the little guy. Once again, I could actually make up numbers. If weight 1 was 10 newtons, weight number 2 would be 80 newtons. 8 times weight number 1. All right, and I want to find the center of gravity of the system. So the way to find the center of gravity is to balance the object with a force upward. It's like kind of like putting your finger under this thing. So I'm going to put my finger like right here. I don't know where that is exactly right now, but I know it's towards the heavier end. But my upward force has to be like 90 newtons, or 9 times the original weight, because it has to support both weights. Once again, it doesn't really matter, because that will fall out of the problem or cancel out of the problem eventually. And then my distances. I'm going to calculate my torque with reference to point A over here, the center of the small sphere. And I know, what I don't know is how far the center of gravity of the system is, which is right there. That's x, distance to that force. But I know, based on the geometry above, that from point A to where this downward force is 24 centimeters, because it's the 12 centimeters of the rod plus 8 centimeters for the radius of this sphere and the 4 centimeters for the radius of the left-hand sphere, so a total of 24 centimeters. So if I calculate my torque with reference to point A, the clockwise torque would be generated by this force, pulling down, trying to make the whole thing rotate clockwise around point A. So it's that force, 8W sub 1, times that distance, 24 centimeters, equals the clockwise producing torque with reference to point A. This force here is pushing up, trying to make the whole thing rotate counterclockwise. 9 times weight 1 times the distance x, which we don't know. So what's going to happen there is the w's obviously will cancel out. I hope it's obvious. Solve for x, and that will give you how far the center of gravity is from the center of the small sphere. I believe the solution manual has the distance from the large sphere. So you will take that answer, subtract from 24, and hopefully that lines up with the solution manual for the center of gravity of this system of masses.